Learning Outcome 2.6. Determine the impulse response of a continuous system given the input-output differential equation. This is the same as the previous video, but now we're going to consider a different example where you need to use the ramp response. Here's another example, very similar to the one we had before, but look at the right-hand side, x prime minus 2x of t. Remember, we're trying to find our impulse response. That's the response of our system when the input is an impulse. That means that the output is going to be an impulse response. We can substitute in h double prime plus 3h prime plus 2h equals delta prime minus 2 delta of t. Just like the last video, we said that we're going to try and doing that, but it's just not going to work because we got that delta prime and that delta on the right-hand side, and we don't know how to do the particular solution for that. So we're not going to try and find the h of t. So last time we said let's try to find the step response. That's where the input is a step function, therefore the output is going to be a step response. We write our equation with a step response, replace our inputs with a step function, find our homogeneous solution, which means we turn the right-hand side to 0, find the characteristic equation. Now we have to find the variables a and b. We'll do that after we get the particular solution. Particular solution, we look at the right-hand side, the forcing function. But our forcing function is now delta of t minus 2 because of that derivative in the x. The derivative of u is delta function. So how do we find that particular solution? That's the same place we were at in the middle of the previous video. So just like last time, we said if our input was an impulse, we get an impulse response. That didn't do us good enough, so we integrated on both sides. If the input is a step function, we get a step response. Now we're going to look at if the input is a ramp function, what's the ramp response? This is because the step function is a derivative of the ramp function, or inversely, the ramp function is the integral of the step function. The ramp is defined to be t when t is greater than or equal to 0, and 0 when t is less than 0. The ramp function is also tu of t. Start over the same way we did the previous problem. Instead of finding y, we're going to find yr. Instead of the input being x, the input is r. Now let's look at our particular solution. The homogeneous is going to stay the same because what's on the right-hand side was set to 0. yr double prime plus 3yr prime plus 2yr is our forcing function. And on the right-hand side, we have a 1 minus 2t. That's because the derivative of the ramp is 1. The ramp is t when t is greater than 0. Derivative of t is 1. If our forcing function is linear, then our particular solution is going to be linear. k1t plus k2. Now we got to find those variables. Take the derivative of our particular, double derivative of our particular. Plug everything in. Can you solve for k1 and k2? Here we go. Our ramp response is the sum of our homogeneous solution and our particular solution. Our homogeneous from before is a e to the minus t plus b e to the minus 2t. We said that our particular solution was going to be linear, k1t plus k2. We solved already for our k1 and k2. Now we need to find a and b. Recall that comes from our initial conditions. The initial conditions are going to be the same as before, 0, from initial rest. Two equations. Please pause the video and solve for a and b. A equals -3, b equals 1. We now substitute those values into our ramp response. We've now solved for our ramp response. Well, remember, we're not looking for the ramp response, we're looking for the impulse response. So just like before, our impulse was the derivative of our step, therefore our impulse response is the derivative of our step response. Now, our step is the derivative of our ramp, so our step response is the derivative of our ramp response. We go from a ramp response to a step response. We go from our step response to our impulse response. Before we had to do one step, now we have to do two steps. We know what our ramp response is. Our step response is the derivative of our ramp response. Remember to use product rule. Your solution is incorrect if you do not use product rule. Apply the no-name theorem to the left-hand term of that derivative. Again, it dropped out. It doesn't always drop out, but it often drops out. Work it out. Don't assume. Now that we have our step response, we again go that previous step to go one back further. Given our ramp response, we got our step response. Now to find our impulse response as a derivative of our step response, use that product rule, use no-name theorem, and there we go. Again, work it out, check that that term actually goes to 0. While it often does, it does not always. We have now solved for our impulse response for a differential equation. It's the same as in the previous video. What was different is that the right-hand side had a derivative in it. So instead of just finding the step response, we had to find the ramp response. If there were to be two derivatives on the right-hand side, we'd have to go from the ramp response one level higher to a quadratic response. Once we find the responses, we have to go back the same number of responses as we had to go forward in finding our solution. It gets us around the tricky part of having a particular solution which has an impulse in it. The mathematics doing that is possible, but it's complicated. This method is a little bit simpler. Plus, there are good physical reasons for using a step response and a ramp response in a physical system.